All right, buckle up, because today we're diving headfirst into the world of decentralized systems.
Ooh, exciting.
It is exciting.
It is exciting stuff.
We're talking Bitcoin, we're talking Nostr,
Yeah.
two very different approaches to a world where nobody's in charge. Get this, nobody's in charge.
You'd think that would make things simpler, wouldn't you?
Yeah, you would think.
But trust me, it creates a whole new set of challenges when it comes to building systems that actually work.
Right, because if something goes wrong, who are you going to call?
Exactly.
Ghostbusters isn't going to cut it.
You're on your own.
Yeah, exactly. So luckily, you've got a stack of sources here that promise to help make sense of it all. We've got a deep dive on Nostr from, get this, the French Bitcoin website, Découvre Bitcoin.
Okay.
Some technical stuff about something called Apache Kafka from way back in 2013. All right. And even some Wikipedia, just sprinkled in for good measure.
Don't underestimate Wikipedia,
Never.
especially when it comes to these kinds of topics. Don't let the variety fool you, though. These sources connect in some really surprising ways. We're going to see how these decentralized systems, they make choices about data, and those choices have huge implications for how they work out in the real world.
That's what we're here to find out.
Yeah.
So the first thing on our agenda is this thing called the CAP Theorem.
Okay.
It sounds a bit intimidating, I'll admit, but from what I understand, it's like the fundamental rule book for understanding, well, any distributed system, right?
Really is. The CAP theorem basically says that if you've got a system where data is spread out, like across multiple servers, you can't have it all.
Okay.
You have to make trade-offs.
Ooh, I like where this is going. Tell me more. What kind of trade-offs?
So the CAP theorem focuses on three properties: consistency, availability, and partition tolerance. And a distributed system can only guarantee two of these at any given time.
Okay, I'm going to need a little more than that. Break those down for me. What do each of those even mean in plain English?
Sure, so think of consistency like this. Imagine you're editing a Google Doc with a friend.
Okay.
Consistency means that you're both seeing the same version of the document at the same time, even if you're making changes in real time.
So no weird moments where I'm looking at an old draft while they're on the latest version?
Exactly.
Gotcha.
Yeah. What about availability?
Availability is all about the system's ability to respond to your request no matter what.
Even if there are failures happening in the background, like behind the scenes, you should still be able to access what you need.
Yeah.
So in that Google Docs example, even if your internet connection gets spotty, you should still be able to open and edit the doc.
Makes sense. So last but not least, we have partition tolerance, which, to be honest, sounds a bit like something out of Star Trek.
It does. It does. A little bit dramatic, isn't it?
Yeah.
It's not quite as dramatic as it sounds.
Okay.
Partition tolerance simply means that the system keeps working even if communication between different parts of the system is disrupted.
Okay.
So it's like if a few servers in a data center go offline, the entire system shouldn't come crashing down.
Right.
It should just keep chugging along.
Okay.
Yeah.
Now I'm starting to see why this is such a big deal. But if you can only have 2 out of 3 of these things, that feels like a pretty major limitation, right? Isn't there some way to cheat the system?
Believe me, if there were, we wouldn't be having this conversation.
Right.
It's a fundamental trade-off, you know?
Right.
In a perfect world, of course, we'd want it all.
Sure.
Consistent data, constant availability, and the ability to just handle any disruption, like no problem.
Right.
But in the real world, networks are messy.
Yeah.
Things go wrong. And when those disruptions happen, you have to choose what's most important.
So it's about priorities.
Yeah.
It's like choosing between 3 amazing superpowers, but you can only pick 2.
Exactly. Let's say a network cable gets cut, right?
Right.
And suddenly parts of your system can't talk to each other. Do you prioritize making sure everyone still has access to the data, even if it means the data might be temporarily out of sync?
Okay.
Or do you say, hold on, everyone, pause everything until we make sure all the data is consistent?
Right.
Even if it means that parts of the system are temporarily offline.
Tough choices.
Tough choices.
So how does this all play out in the real world?
That's where things get really interesting.
Okay.
That's where things get really interesting. Let's bring in that technical source you mentioned earlier, Apache Kafka.
Kafka, right. The platform designed to handle massive amounts of data in real time.
Yeah,
Like social media feeds, financial transactions, that kind of thing.
exactly.
Okay.
And that LinkedIn engineering blog post you've got there, that's going to show us how Kafka grapples with these CAP theorem trade-offs.
So with all that data flying around, Kafka needs a way to make sure that information is both easy to get to
Right.
and accurate.
Right, and accurate, yeah.
No easy feat.
No easy feat at all.
So how do they do it?
Right. That's where replication comes in.
Okay.
Instead of storing just one copy of the data, Kafka creates multiple copies, we call these replicas,
Uh-huh.
and spreads them across different servers.
So it's like having backup copies in case one server decides to take a nap.
Exactly. That's a great way to put it.
I got it. Okay, I'm with you. But how do they make sure those replicas don't get out of sync? Because if you've got multiple copies
yeah,
and they're all changing.
you're thinking like a true distributed systems engineer. Keeping those replicas in sync, that's exactly where the consistency part of the CAP theorem comes into play.
Okay.
Kafka aims for strong consistency.
Strong consistency, meaning all those replica copies have to be identical
Yes.
at any given time.
Yeah, that's the goal.
That sounds like a logistical nightmare.
It's definitely a challenge. But Kafka has some clever tricks up its sleeve. It uses something called a leader-follower approach.
Okay.
One replica is the designated leader.
Okay.
For a specific piece of data,
Gotcha.
any write request goes straight to that leader,
Okay.
and then the leader replicates those writes to its followers, keeping everyone in the loop.
Okay, so one replica calls the shots,
That's right.
and the rest follow suit.
Yeah,
But networks aren't exactly known for their reliability.
that is true.
So what happens if a follower lags behind or goes offline?
You've hit upon a very critical point.
I knew I was good for something.
Kafka can't wait around forever for every single follower to confirm that they've received the message.
Right.
That would slow things down way too much.
Like if one follower is having a bad day,
Yeah.
you don't want the whole system to grind to halt.
Exactly.
Right.
Exactly. So Kafka walks this tightrope with something called an in-sync replica set,
Okay.
or ISR for short.
ISR, got it.
It's a dynamic group of followers that Kafka knows are up to date with the leader.
So it's like the VIP club
Yes, exactly.
of the most reliable followers.
You could say that. Here's the kicker, though.
Okay.
The leader only considers a write operation committed when the replicas in its ISR have acknowledged that they received the data.
So instead of waiting for everyone to RSVP,
Yes.
they're just waiting for the VIPs to RSVP?
Precisely.
Okay, I think I'm following. So instead of waiting for everybody, Kafka waits for confirmation from, like, its A team of replicas.
Exactly.
That makes sense, right?
It does.
It's a balance between speed and making absolutely sure the data is consistent.
Yes.
But let's zoom out for a second.
Okay.
You've got Kafka and its ISR, but where does this all fit into the bigger picture of the CAP theorem?
Excellent question. By obsessing over strong consistency and going to these lengths to make replication work smoothly within a data center, Kafka is basically placing its bets on consistency and partition tolerance. It's a CP system at its core, at least within a single data center.
Okay, so because in a data center,
Yeah.
network issues are less likely, so they can afford to prioritize consistency over everything else.
Exactly.
Yeah.
They're willing to sacrifice a bit of speed to ensure that the data is always reliable and in sync.
So Kafka plays it safe,
It does.
prioritizing consistency within a controlled environment.
Yeah, you could say that.
But what happens when you take that desire for consistency to, like, a global scale? Like with Bitcoin.
Now, that's where things get really wild.
Yeah.
Remember how we talked about the CAP theorem and having to make trade-offs? Well, Bitcoin takes a very different approach than Kafka.
Okay.
It prioritizes availability and partition tolerance over strict consistency.
Wait, hold on. Bitcoin, the system that everyone praises for its security
I know.
and immutability, is willing to tolerate some inconsistency in the data?
To a certain degree, yes.
That seems counterintuitive.
It might seem strange at first, but it's crucial to understand that Bitcoin is playing a different game than Kafka. Bitcoin is all about being a global, unstoppable force
Right.
for peer-to-peer payments. It needs to stay online no matter what, even if parts of the network go down or someone tries to mess with the system.
So even if, like, a giant squid decides to chew on an undersea internet cable,
Exactly.
Bitcoin just keeps on trucking.
Precisely. Now, to truly appreciate the brilliance of this, let's imagine a scenario.
Okay.
Picture two Bitcoin miners, miles apart,
Okay.
adding blocks to the blockchain at practically the same time.
Okay, I'm picturing it. Two miners racing to solve those cryptographic puzzles, totally unaware of each other.
Exactly. Because, you see, information takes time to travel across the network,
Right.
even at the speed of light. So some nodes might see one version of the blockchain first, while others see a slightly different version. And this, my friend, is what we call a fork. A fork in the road.
So for a brief moment, there are two competing versions of the truth
Yes.
floating around the Bitcoin network.
That's right. It's like a split in the road of the Bitcoin timeline.
Right.
But fear not. This is where Bitcoin's secret weapon, its consensus mechanism, proof of work swoops in to save the day.
Okay, you're going to have to break this down for me.
Okay.
How does proof of work resolve this conflict
Okay.
and bring everyone back to a single version of the truth?
Think of it like this. Eventually, one of those forked chains will become longer, meaning more computational power, more work has been invested in it. And that, my friend, is the chain that wins.
Okay.
The Bitcoin network agrees to accept the longest chain as the true history,
Okay.
and the blocks on the shorter fork are discarded.
So it's a bit like a democratic vote, but instead of counting ballots, you're counting how much computing power has been poured into each version of the blockchain.
You got it. And that, my friend, is how Bitcoin achieves what we call eventual consistency.
Eventual consistency. So everyone gets on the same page, but it might take a little bit of time.
Exactly. It's a brilliant compromise.
Right.
By prioritizing availability and partition tolerance over instant, unwavering consistency, Bitcoin can survive almost anything.
Right.
It's like the cockroach of financial systems,
Wow.
practically indestructible.
Okay. I'm starting to see the method behind the madness.
Yeah.
But now I'm really curious about Nostr.
Yeah.
We've got Kafka, the champion of strong consistency in a controlled environment. And we've got Bitcoin, the master of availability and eventual consistency on this global scale.
Yes.
So where does that leave Nostr? Our decentralized social media hopeful.
Ah, Nostr.
Yeah.
Like the rebellious younger sibling trying to forge its own path in the decentralized world.
Yeah.
You see, Nostr, just like Bitcoin, is designed with decentralization and censorship resistance in its DNA. But instead of relying on a blockchain, it relies on something quite different. A network of independent relays to store and distribute data.
Independent relays. So instead of the single global ledger,
Yeah.
Nostr is more like a network of interconnected nodes, each holding their own piece of the puzzle.
You're catching on quickly. So if you're using a Nostr app and you send a message, it gets distributed to all these different relays. Anyone who wants to see your message can then access it from any of those relays. No central server, no single point of failure.
Okay, that's pretty cool. But how does Nostr deal with the CAP Theorem dilemma? Which 2 out of 3 is it choosing?
Well, based on what we know about how Nostr is designed, it seems like it's leaning towards an AP approach, just like Bitcoin.
Okay.
Each relay is like its own little island of data.
Okay.
They chat with each other, they share information,
Right.
but there's no ironclad guarantee that they'll always be perfectly in sync at every single moment.
Okay.
And that, my friend, leads us down a very interesting path.
Okay, now you've really got my attention. Tell me more about this interesting path. What are the implications of Nostr's approach? What are the potential benefits and drawbacks?
Yeah.
All right, so we've got these two decentralized systems, right?
Right.
Both, it seems, leaning towards availability and partition tolerance.
Yeah.
But they go about it in very, very different ways. Bitcoin, with its blockchain, this global, synchronized ledger, carefully maintained by miners all over the world.
Yeah.
And then there's Nostr, with its network of independent relays, each holding their own little piece of the data puzzle.
Right, right.
What are the trade-offs of each approach? What does it actually mean in practice for someone using these systems?
That's the million-dollar question, isn't it?
Yes, yeah.
Bitcoin, by going all in on this single, globally consistent blockchain, achieves this incredible level of security and immutability. I mean, think about it. To tamper with the Bitcoin blockchain, you would need to control a majority of the entire network's computing power.
Which, let's be real, is about as likely as me winning a staring contest with 1,000 cats simultaneously.
Exactly. So it's really a testament to the power of decentralization and, these cleverly designed incentives.
Yeah,
But you knew there was a but coming, didn't you?
always a but.
The security and consistency, they come at a cost.
Okay.
Bitcoin transactions can be quite slow, especially during peak times.
Right.
And those transaction fees,
Oh, tell me about it.
they can really add up.
Yeah, it's like trying to send a package during the holiday season.
Right.
It'll get there eventually, but you might have to shell out extra for those expedited shipping fees.
A perfect analogy. Now, Nostr, on the other hand, with its network of relays, prioritizes speed and flexibility.
Okay.
Setting up a relay is relatively easy. Anyone can do it with a little bit of technical know-how.
Right.
And because there's no central point of failure, Nostr is incredibly resilient
Yeah.
to censorship.
So it's like sending a message through a network of friends,
Yeah.
each willing to pass it along rather than relying on a single postal service.
Precisely. And you knew there was a but coming with Nostr too, right?
There's always a but.
This approach comes with its own set of question marks.
Okay, like what?
Well, for example, remember how Bitcoin has that built-in economic incentive?
With the mining rewards, right?
With the mining rewards,
Yeah.
yes. The miners are incentivized to play by the rules because that's how they earn Bitcoin.
Right, like a self-sustaining ecosystem.
Exactly.
Yeah.
Nostr, as it stands, doesn't have that same kind of built-in economic model for its relays.
So it's more of a volunteer effort right now.
In a way, yes.
Okay.
And that raises some interesting questions about long-term sustainability.
Right, because who's going to pay for the bandwidth,
Exactly.
the storage, the equipment, the electricity?
All the behind-the-scenes stuff that keeps those relays running.
Yeah,
It's a challenge that the Nostr community is grappling with right now.
for sure. And what about spam?
Yeah.
Because if anyone can just spin up a relay,
Yes.
wouldn't that make Nostr like a spammer's paradise?
That's another very valid concern. Découvre Bitcoin, that French website you shared, highlighted this very point.
Okay.
Nostr relies heavily on kind of community-driven solutions for things like spam prevention and content moderation.
So instead of relying on algorithms or like a central authority to kind of filter out the junk,
Right.
it's more about like users flagging bad content and relays deciding which voices to amplify and promote.
Exactly.
Ooh.
It's a trust the community approach.
Right.
Which, as you can imagine,
Mm-hmm.
has its own set of complexities
Right, yeah.
and potential pitfalls.
Sure, sure. It's fascinating how both of these systems, while striving for this ideal of decentralization,
Yes.
end up making such different choices with different strengths and weaknesses.
Right.
It's like they're two sides of the same coin.
That's a great way to put it. And that's the beauty of this whole space.
Yeah.
It forces us to confront these fundamental trade-offs.
Yeah.
To think critically about what we value most in a system.
Right.
There's no magic bullet. There's no one-size-fits-all solution.
It's a bit like choosing between a sturdy, reliable off-road vehicle and like a nimble, fuel-efficient sports car.
Right.
Both can get you where you need to go, but the best choice depends entirely on like your needs and your priorities.
Exactly. And who knows, maybe the future holds some incredible hybrid approach, right?
Ooh.
A system that combines the security and immutability of a blockchain with the flexibility and speed of a distributed network of relays.
Now that's a tantalizing thought.
Wouldn't that be something?
The best of both worlds.
Yeah.
Well, listeners, there you have it. A whirlwind tour of decentralized systems, from the theoretical underpinnings of the CAP Theorem
Right.
to the real-world implementations of Bitcoin and Nostr.
Yeah.
We've seen how these systems grapple with the challenge of achieving consistency, availability, and partition tolerance in a world where no one is in charge.
It's not easy.
Yeah.
That's for sure.
As you continue to explore this exciting world of decentralized technologies, remember to ask those tough questions.
Yes.
Challenge those assumptions. Keep your mind open to the possibilities.
Because who knows? You might be the one to design the next groundbreaking decentralized system.
That's right. Until next time.
Until next time.